Welcome back to QHSE Talks.
Yeah.
Usually when we talk about a medical diagnosis in the workplace, there's this expectation of absolute, undeniable precision.
Right, like it's a math problem or something.
Exactly. It's almost like mechanical engineering. You fall off a ladder, you break your arm, the x-ray goes up on the light box, and you see that jagged white line across the radius bone.
Yeah, it's right there in black and white.
Right. The doctor points at it, you point at it, and there is this shared objective reality. It's totally binary, broken or not broken.
It's comforting in a really strange way. I mean, we like occupational hazards to be visible.
Yeah.
We want to categorize the damage, put a cast on it, count the days to recovery, and just move on.
But then you step into the world of occupational health and specifically the realm of neurodevelopment, cumulative trauma, and musculoskeletal disorders. And suddenly that x-ray machine is just completely useless.
You're flying blind.
We're looking at a diagnostic landscape that is just incredibly murky. I mean, imagine a worker, let's call him, an anonymous machinist, or maybe even like a data entry clerk.
Sure.
For 10 years, they've been doing the exact same motion, reaching slightly up and to the right to pull a lever, or leaning slightly forward to read a monitor.
Right, every single day.
Every day. There is no sudden snap. There is no pool of blood. But one morning, they wake up and they physically cannot close their hand.
Yeah, it just stops working.
The tendons are so frayed, the sheath is so inflamed that this biological machine has just quietly, invisibly ground to a halt.
It is the absolute definition of diagnostic muddy waters because you can't point to a specific second in time when the injury happened.
Right. There's no incident report for that exact moment.
Exactly. The injury was the culmination of 3 million micro-movements over a decade. And by the time the worker actually reports the pain, the structural damage is already profound.
And that silent, invisible breakdown is exactly why today's QHSE Talks session on our sources is so critical.
It's vital.
We are doing a highly specialized, laser-focused session designed specifically for you, the safety professional. If you are listening to this right now, there is a very good chance you are preparing for the Associate Safety Professional exam, the ASP exam.
Which is a beast of a test.
It is. And today we are zeroing in on one of the most vital, practical, and heavily tested areas of the exam blueprint. We're talking about Domain 3.
Domain 3, which covers ergonomics.
Yes, and specifically Topic 4, which is
Okay.
Apply Ergonomic Principles for Workspace Design.
This topic is just relentless in its scope. I mean, it covers everything.
Everything.
In-office layouts, remote work setups, rugged field environments, intricate assembly stations, laboratory bench hoods. It is this massive area of professional practice that dictates exactly how human beings physically interact with their livelihood.
It really is. And to help you master this, we have a massive stack of sources on the table between us today.
We really do. I'm looking at a mountain of paper here.
I know, right? We are pulling directly from the ASP Blueprint documents, the Handbook of OSHA Construction Safety and Health, heavy-hitting engineering textbooks like Brower's Safety and Health for Engineers,
A classic.
and Flieger's Industrial Hygiene Reference, plus a bunch of intensive exam study guides and question banks, including materials from Bowen EHS. But I really want to reframe how we look at this stack of paper.
How so?
Mastering this material isn't just about memorizing facts to pass multiple choice tests.
Oh, far from it. If you treat this as just exam prep, you're missing the entire point of the profession.
Exactly.
This is about fundamentally understanding how to adapt the physical world to the limits of the human body. When you truly grasp these concepts, you gain the ability to step onto a factory floor or into an office building and see invisible forces.
Like Neo in the Matrix, right?
Yeah, basically, yeah. You see biomechanical stress, leverage, static load. You gain the ability to prevent devastating long-term injuries before the concrete for the factory floor is even poured.
It's a literal superpower. You are engineering human longevity. So let's unpack this from the ground up. Let's start by demystifying the word itself, ergonomics.
Okay, let's do it.
I feel like the word has been totally hijacked by marketing departments. Like when most people hear ergonomics, they just think of a really expensive, fancy office chair with a dozen plastic levers that cost $1,500.
Or a keyboard shaped like a wave.
Yes, the wave keyboards.
Yeah.
But looking at the Brower and Flieger texts, this is actually a massive, rigorous engineering and management discipline, isn't it?
The commercialization of the word definitely dilutes its actual scientific weight, for sure. To understand what it truly means for your profession, we have to look at the etymology of the word itself.
Which is highlighted in Flieger's reference, right?
Exactly. Ergonomics comes from two Greek words, ergos, which translates to work, and nomos, which means law.
The laws of work. Wow. That sounds a lot heavier than a nice lumbar cushion.
Right. It implies non-negotiable physical realities, just like the laws of thermodynamics or, gravity. The laws of work dictate that if you subject biological tissue to loads and frequencies beyond its capacity, it will fail.
It will break down.
It has to. Ergonomics is a multidisciplinary science. It pulls from biomechanics, psychology, engineering, and physiology to assemble information on human capacities and capabilities.
Okay, so it's bringing all these hard sciences together.
Yeah. And the core non-negotiable principle here, the absolute golden rule you must internalize for the exam and your career is that the job must be adapted to fit the person.
Not the other way around.
Never the other way around. You never, under any circumstances, force the person to fit the job.
I want to pause on that because it sounds simple, but historically, industry did the exact opposite, didn't it?
Absolutely.
During the early Industrial Revolution, and even well into the mid-20th century, we built the machines first. We built these massive steel looms and presses to optimize production, and then we just sort of wedged the human being into whatever gap was left over.
Yeah, that was the defining characteristic of what the texts call reactive ergonomics. We operated on a model where the machine was the fixed variable,
Right.
and the human was the adaptable variable. We waited for someone to get hurt, for an injury to be reported, or for a worker to physically break down.
And then what? We just band-aided it.
Pretty much. Then maybe we handed them a pair of gloves or put a piece of foam on the edge of the table and called it a fix.
And what the sources emphasize now is this necessary, mandated shift to proactive ergonomics, which is where you, the safety professional listening to this, come in.
Exactly. This means considering the biological user from the very outset of facility design.
You're reviewing blueprints, evaluating product development cycles, auditing purchasing catalogs before a single tool is even bought. But let me push back on this just from a management perspective. If I'm a CEO, proactive ergonomics sounds incredibly expensive. You're telling me I have to redesign my entire assembly line before it's even built, just so someone doesn't get a sore shoulder in 5 years.
And that is exactly the pushback you will face in the field. But the study guides give you the ammunition to defeat that argument.
Okay, lay it on me.
Proactive ergonomics is not some charity initiative, right? It is a massive economic driver. The texts make it very clear. Work that is well designed intrinsically impacts quality and productivity.
How so? Connect those dots for me. Like, how does saving a shoulder make me money?
Okay, so when you optimize the human-machine interface, you eliminate wasted motion. If a worker isn't constantly fighting their workstation, reaching too far, squinting to see a gauge, twisting their spine to grab a part, they work faster.
They aren't wasting seconds on every single cycle.
Right. And you reduce training time because the workflow is intuitive. You drastically minimize errors because fatigue actually causes cognitive decline and physical mistakes.
So fewer messed up parts, less scrap.
Exactly. You are actively fighting worker fatigue and boredom. From a purely financial standpoint, the return on investment for proactive ergonomic design is staggering.
When you calculate the reduction in workers' comp claims.
Right, workers' comp, scrap rates, turnover, it is a massive competitive advantage.
So to properly design that interface, to understand why we can't just, buy that fancy office chair and call it a day, we have to thoroughly understand the biological machine we are trying to protect.
We do.
Which brings us to the human body itself and the biomechanics of work. We are sort of stepping out of the management suite and into the anatomy lab now.
The physical ergonomics section of the ASP exam focuses heavily on human anatomical, anthropometric, physiological, and biomechanical characteristics.
That's a lot of syllables.
It is, but you absolutely need to know the difference between the two main pillars mentioned in the study guides, anatomy and anthropometry. They sound similar, but they serve completely different functions in workspace design.
Okay, let's draw a hard line between them for you, the listener, right now. Anatomy is the study of body structures. It's the hardware.
Right.
We're talking about the skeletal system, the muscle fibers, the tendons, the ligaments, the synovial fluid. It's understanding how a joint is physically constructed and how it actually bears a load.
And anthropometry, on the other hand, is the study of human dimensions. It's the physical measurements of a population.
So like a Tape measure?
Basically, how long is the distance from the elbow to the fingertips? How tall is the sitting torso? What is the functional reach radius of, say, a 5th percentile female versus a 95th percentile male?
So it's population data.
Yeah, anthropometry provides the statistical data regarding the physical size and shape variations across the global population. You use this data to design equipment that actually fits the people using it.
So to put them together in a practical scenario, if I'm designing a control room console, anthropometry tells me the exact statistical probability of how high I need to put the desk so that 90% of my workforce can fit their knees under it.
Yes, exactly.
But anatomy tells me what is physically happening to the lumbar spine and the discs if I get that measurement wrong and force them to hunch over.
That is the perfect synthesis. Anthropometry gives you the dimensions. Anatomy tells you the biological cost of ignoring those dimensions.
Makes sense.
And when we fail to combine those two sciences properly, we introduce the biggest, most prevalent hazard in workspace design: awkward postures.
Which are everywhere.
Everywhere. The overarching goal of every ergonomic intervention is to keep the body in what is called a neutral posture.
The sources mention a very specific, easily testable example for the hands and wrists when defining neutral posture. They call it the handshake position.
Yes, and it's a brilliant way to visualize it. If you hold your arm out right now, as if you are about to shake someone's hand, notice what your wrist does.
Okay, I'm doing it. It is completely straight.
Right. It's not bent upward, which is called extension. It's not bent downward, which is flexion. And it's not cocked to the left or right, which would be radial or ulnar deviation.
It's just perfectly aligned with my forearm.
That handshake alignment is the ideal neutral posture for the wrist.
What biologically is happening in that neutral handshake state that makes it so safe? Like, why does the body prefer that?
Well, in that neutral posture, the muscles, tendons, and ligaments are at their natural resting length. The carpal tunnel, which, is an actual physical tunnel of bone and ligament in your wrist, is as open as it can possibly be.
So there's maximum clearance inside.
Exactly. The flexor tendons can glide smoothly back and forth, and the median nerve is completely uncompressed. Because everything is aligned, the muscles can generate maximum force efficiently without pinching nerves or restricting vital blood flow.
Now let's contrast that with the bad stuff.
Yeah.
The sources highlight something called flexion, and they seriously warn against designing workstations that force it.
Flexion is a classic awkward posture. In the context of the wrist, it's where the palm faces downward and the fingers curve slightly inward toward the underside of the wrist.
Think of typing on a keyboard that is placed much too high on a desk, where you have to drop your wrist down sharply to reach the keys.
Right, your forearms are angled up, but your hands are angled sharply down.
Like a T-Rex almost.
Yeah, exactly like that. That constant flexion puts immense structural stress on the wrist. The tendons are now rubbing against the walls of the carpal tunnel.
Because they're bending around a corner.
Exactly. The median nerve is being compressed. The synovial sheath, which is the fluid layer that surrounds the tendons to reduce friction, starts to get irritated and inflamed.
Which leads to pain, swelling, and eventually a full-blown musculoskeletal disorder like carpal tunnel syndrome.
Exactly.
But here's where it gets really interesting to me and where the physics of the human body becomes, fascinating. It's not just the position of the body that causes damage. It's the effort required to hold it there.
Oh, the effort is huge.
The sources draw a massive underlying distinction between dynamic effort and static effort.
This is a crucial concept, not just for the ASP exam, but for any safety professional auditing a factory floor. You have to be able to identify these two types of effort.
Let's break them down.
Dynamic effort involves movement. The muscles contract and then they relax. They contract and relax. This rhythmic action acts almost like a biological pump.
Okay, a pump.
Yeah. When the muscle relaxes, blood flows in, bringing fresh oxygen and glucose. When it contracts, it pushes blood out, flushing away metabolic waste products like lactic acid.
So dynamic work is somewhat self-sustaining, provided the load isn't too heavy and the pace is reasonable. The body is cleaning up after itself as it works.
Precisely. Static effort, on the other hand, is the biological enemy.
The enemy. Why?
Static work is defined as the prolonged contraction of muscles, where a body part is held in one fixed position for a long duration. There's no movement, just constant tension.
Let me throw an analogy at you to see if the biological mechanics track here, because this is vital to understand.
Go for it.
Let's say I go to the grocery store and buy a gallon of milk. If I hold that full gallon of milk right against my chest, tucked in tight to my center of gravity, I could probably stand there chatting the aisle for 10 or 15 minutes without too much trouble, right?
Sure, easily.
But if I take that exact same gallon of milk with the exact same mass and I lock my elbows and hold it straight out in front of my body, parallel to the floor,
Oh, man.
my shoulders are going to start screaming in about 60 seconds. My arms will start shaking and I will physically have to drop it. The weight of the object hasn't changed by a single ounce, but the static effort of holding it out away from my body completely destroyed my muscle endurance. Why does that happen so fast?
The mechanics behind your milk analogy are exactly what causes widespread industrial injuries. Two things are happening there. First, the biomechanical load multiplies drastically as the lever arm gets longer.
A lever arm. Okay.
When the milk is at your chest, the distance from the load to the pivot point, which is your shoulder and spine, is virtually zero. When you extend your arms, that lever arm is now maybe 2 feet long.
So it acts like a crowbar against my shoulder.
Exactly. The torque on your shoulder joint and your lower back increases exponentially. Your muscles have to fire significantly harder just to hold the same weight.
And the second thing,
Blood occlusion.
which means blocking the blood.
Right. Because you are holding a static posture, your muscles are in a state of continuous contraction. When a muscle contracts beyond about 15 to 20% of its maximum voluntary capacity, the physical pressure of the muscle fibers actually clamps down on the capillaries inside the tissue.
Whoa. The blood vessels are pinched shut.
It's cut off. And even worse, the metabolic waste products have nowhere to go. Lactic acid builds up rapidly in the localized tissue.
Because there's no pump action to clear it out.
Exactly. This leads to severe acute fatigue and actual cellular tissue damage much, much faster than dynamic work. The worker feels it as a burning sensation and extreme fatigue. That is why static postures are the ultimate ergonomic hazard.
That is terrifying when you realize how many jobs require people to just stand and hold things.
Yeah.
So how do we fix this in the real world? The OSHA construction text gives some amazing examples of engineers and tool designers actively fighting static posture through brilliant design.
They do, and you really need to look for these engineering controls when you are applying ergonomic principles to workspace design. One great example from the field is the development of self-feeding screw guns for construction and assembly.
Oh, I've seen those.
In the past, a worker had to use one hand to hold the screw perfectly in place, acting as a human vice, which is a stressful, high-precision static posture, while the other hand operated the heavy drill.
And doing that hundreds of times a day means one hand is constantly under static tension, restricting blood flow.
Exactly. A self-feeding screw gun engineers that hazard entirely out of the process. The tool feeds the screws automatically. It completely frees up that holding hand, eliminating the static load on the secondary arm.
Another phenomenal example from the text is the use of extra long shafts on drills or drivers. Imagine you are on a construction site or doing maintenance in a facility, and you have to drill dozens of holes into a concrete ceiling.
A nightmare ergonomically.
Historically, you raise your arms above your head, pushing a heavy drill upward.
Yep.
That is a horrific static overhead posture. Your shoulders are bearing the weight, the lever arm is extended, and your neck is craned back.
It's a recipe for severe rotator cuff degradation and cervical spine compression.
But by providing a tool with an extra long extension shaft, the worker can stand on the floor, look straight ahead or slightly upward, and hold the motorized, heavy part of the tool down at their waist or chest level. The long shaft reaches the ceiling for them.
You are bringing the work into the worker's neutral zone. You're adapting the tool to the physical limitations of the person, rather than forcing the person to adapt their skeletal structure to the height of the ceiling.
That is the essence of proactive ergonomics right there. You engineer the hazard away. Okay, so knowing that static effort and awkward postures are the ultimate biological enemies, how do safety professionals actually lay out a workstation to defeat them? If I have an empty room and a list of tasks, how do I physically arrange the environment? Let's say I'm looking at a hypothetical chemical mixing station or a complex manufacturing bench. Where does everything go?
Well, when you're designing a space from scratch, whether it's a vehicle dashboard, a manufacturing bench, or a laboratory hood, you can't just place things where they fit best aesthetically.
Right, you can't just make it look nice.
You have to rely on proven ergonomic frameworks. To do this, we look to the 4 general principles for component workstation layout defined by Sanders and McCormick. These are heavily featured in the Brower engineering text.
Let's use a scenario to explore these. Imagine a terribly designed, chaotic control room in a processing plant. Dials are everywhere, buttons are hidden behind monitors, and the operator looks like a frantic octopus just trying to run the system.
I've audited that exact room, trust me.
I'm sure you have. We're going to use these 4 principles as a forensic toolkit to explain why it's failing and how to rebuild it organically. Principle number 1 is the importance principle.
The importance principle simply dictates that the most critical items go in the most accessible, optimal locations. It sounds obvious, but it is violated constantly.
Oh, yeah.
If a control is vital for the safe operation of a machine, or vital to the primary objective of the job, it needs to be placed exactly where the operator can reach it instantly, without looking, stretching, or shifting their body weight.
So in our chaotic control room, the emergency stop button shouldn't be tucked away on the far right corner of the desk behind a coffee mug. It has to be prime real estate, dead center, immediate reach.
Exactly. But wait, if everything important is right in front of them, doesn't the workspace get incredibly cluttered?
That's a good point. If 10 things are important, they can't all be dead center.
Right. How do you balance the importance of a component with how often it's actually touched?
That brings in the second tool in the forensic kit, the frequency of use principle.
This principle is about efficiency and preventing cumulative wear and tear over an entire shift. Things used constantly need to be closest to the worker.
Okay, give me an example.
Let's say our operator has a specific toggle switch they have to flip 50 times an hour to vent pressure. That switch must be right at their fingertips, in the primary reach zone. Conversely, if there is a calibration dial that is very important, but it is only adjusted twice a month during maintenance.
It doesn't need to take up valuable primary real estate.
Exactly. It can be placed higher up or further away. You prioritize the geography of the desk based on how many times the arm has to physically extend.
That makes a lot of sense. You're calculating the biological cost of reaching and minimizing the most frequent trips. Now, what about the cognitive side? Our operator is staring at 50 different gauges. How do we organize them so their brain doesn't just fatigue? That's principle number 3, the functional principle.
The functional principle involves grouping items by what they actually do or the system they relate to. In our control room, if you have 3 dials that control the temperature, pressure, and flow rate of one specific chemical tank, those 3 dials must be clustered tightly together.
You shouldn't have to look at the top left of the panel for the temperature and then scan down to the bottom right for the pressure.
Exactly. Grouping functionally reduces the cognitive load of searching, and it reduces the physical movement of the eyes, head, and neck. The operator can take in the status of that entire chemical tank in one single glance. It creates logical zones of work.
And finally, the 4th tool to fix this room, the sequence of use principle.
This principle is about laying out tools, bins, or components in the exact chronological order the worker will need them.
Left to right sort of thing.
Usually, yeah. If an assembly process requires part A, then part B, then the application of a sealant, the physical bins on the bench should be laid out left to right or right to left in that exact sequence.
It creates a smooth, continuous choreography of motion. You aren't reaching across your body to grab part B from the left, then twisting to the right for part A, then reaching back left for the sealant.
Exactly. It's fluid.
But let me ask you about the mechanics of that. If I lay out 10 bins in a perfect sequence from left to right, how do I avoid creating a setup that forces the worker to constantly reach across their midline or twist their spine? I mean, if everything moves left to right, isn't the right arm doing way more work by the end?
That's a very astute observation, and it's a really common pitfall. The overarching goal of these 4 layout principles, when applied together, is to distribute the tasks evenly.
No.
You want to distribute the biomechanical load between the 2 hands or even between the hands and feet so that one body part isn't taking 100% of the mechanical wear and tear. If you put all the sequential bins on the right side, the right shoulder is bearing the entire burden.
So how do you fix that?
By skillfully applying the sequence of use and frequency of use principles simultaneously, you balance the workstation. Maybe you design it so the left hand retrieves the raw part from a bin, while the right hand simultaneously retrieves the tool to manipulate it.
Oh, so they meet in the middle.
Yes. You eliminate the need for the worker to cross their midline, which is a massive key ergonomic hazard.
It truly is like choreographing a dance. You're designing the physical space to dictate a healthy, symmetrical movement pattern. You are forcing the body into good habits.
Exactly. These 4 component principles, importance, frequency, function, and sequence, dictate where the specific items go on the desk or the bench.
But the physical dimensions of the workstation itself, the height of the table, the type of chair, the lighting above it, dictate how the worker physically exists in that space.
Yes. And that transition from the layout of the tools to the layout of the environment brings us to the absolute core of ASP exam topic 4.
Let's look at the Tray 9A General Workstation Design Principles from the OSHA Construction Handbook. This section of the source material is essentially the Magna Carta of ergonomics.
It really is.
It outlines 13 golden rules for workstation design. Rather than just read a numbered list, let's dive into the physics and reasoning behind the most critical ones.
We cannot overstate how important these rules are for your daily practice. The foundational rule, the one that governs all others, is the mandate for adjustability. The rule states plainly, one size does not fit all. You cannot build a station for the average person.
Because mathematically, the average person doesn't exist. If you design a cockpit for the exact average height, average arm length, and average leg length, you will find that almost zero pilots actually possess all three of those average measurements simultaneously.
Precisely. You have to engineer adjustability to accommodate a wide range of anthropometric data, usually designing to accommodate from the 5th percentile female to the 95th percentile male. You have to enable both small and large persons to fit comfortably and work in neutral postures.
The sources highlight adjustable height pallet platforms as a prime real-world example. Imagine a worker loading boxes onto a shipping pallet.
Okay, I'm picturing it.
When the pallet is empty, it's flat on the floor, so the worker has to bend at the waist, placing massive shear force on their lumbar spine just to place the first box.
Right.
Then, when the pallet is fully loaded, it might be 5 feet high, forcing the worker to lift heavy boxes above their shoulders.
Both extremes are highly hazardous. But by introducing an adjustable hydraulic scissor lift platform under the pallet,
Oh, that's smart.
yeah, the worker can raise the empty pallet to waist height. As they add layers of boxes, they slowly lower the platform. The physical location where the worker places the box never changes. It remains constantly in their optimal power zone, right at waist height.
You haven't just trained the worker how to lift properly. You have engineered the hazard out of the universe entirely.
That is the goal.
That is brilliant. Now, another major rule focuses on locating materials. The text says you must put everything directly in front of the worker to eliminate spinal twisting. I want to drill down on why twisting is so catastrophic. Everyone knows you aren't supposed to twist and lift, but what is actually happening inside the spine?
It's a matter of structural engineering, really. Your spine is made up of vertebrae separated by intervertebral discs. These discs are essentially tough, fibrous rings with a gel-like center, acting as shock absorbers.
Okay, jelly donuts, basically.
Yeah, exactly like jelly donuts. When you stand straight and bear a load, the force is distributed evenly across the surface area of that disc. It can handle a lot of vertical compression. But when you twist your torso, you are applying torsion, a rotational shear force.
Well, you are wringing it out like a wet towel.
Exactly. The fibrous rings of the disc are not designed to handle rotational shear under a heavy load. Torsion weakens the structural integrity of the disc wall rapidly.
Wow.
If you combine bending forward, which pushes the gel center backward, with twisting, you create the exact mechanical forces required to rupture that fibrous wall, leading to a herniated disc.
And that's game over for a while.
It is one of the most common, debilitating, and expensive injuries in industry. Therefore, the rule dictates you must locate materials directly in front and provide sufficient space for the whole body to turn.
So they move their feet.
The worker should pivot their feet to face the work, moving as a single solid column rather than twisting their torso.
Let's talk about the arms. We touched on static load earlier, but the rules provide a very specific metric for reach limits. The principle dictates that primary arm movements or extensions of more than 15 inches must be minimized. Why 15 inches specifically? Where does that number come from?
That 15-inch metric is derived from biomechanical leverage. When your elbows are resting at your sides, your hands are in the optimal power zone. The muscles in your forearms and hands can do delicate or forceful work without taxing the shoulder. Once you extend your hands beyond 15 inches from your body, you are abandoning that power zone. The lever arm of your extended limb becomes significantly long.
So the shoulder muscle specifically, the deltoids and the rotator cuff, have to engage heavily just to counteract gravity and hold the arm up in the air.
Yes, you lose mechanical advantage. The further you reach, the faster the shoulder muscles fatigue and the less precision you have in your fingers. By keeping primary work within a 15-inch radius, you preserve the strength and endurance of the upper body.
And speaking of how the arm moves within that radius, another golden rule is what I call the pivot point. The text says quite emphatically that arm movements should pivot around the elbow, not the shoulder.
This is a major ergonomic intervention that is so easily missed during an audit. Imagine a worker sweeping their arm across a wide table to sort parts.
It's like pushing things into a bin.
Yeah. If the pivot point for that sweeping motion is their shoulder joint, they're constantly engaging the complex rotator cuff musculature, the trapezius, and the upper back and neck muscles. They're moving the entire weight of the arm.
Which leads to massive upper back tension by the end of the shift.
Exactly. But if you design the workstation so the parts are closer and the pivot point becomes the elbow, everything changes. The larger, more complex shoulder joint remains at rest at the worker's side. The smaller, more efficient forearm muscles do the sweeping motion.
It dramatically reduces the biomechanical stress on the upper back and neck. It's about isolating the movement to the most efficient joint.
Precisely.
The rule also mentions the quality of the movement. It states that movements should be continuous and curved, not straight line and jerking. It's better to have a smooth arc of motion than abrupt stops and starts.
Because abrupt stops require antagonistic muscle groups to fire rapidly to act as a brake. A smooth, sweeping curve utilizes the natural momentum of the limb, requiring far less muscular effort.
Let's transition to a seemingly mundane piece of equipment that is actually a complex ergonomic tool. The chair.
The chair.
The rules give very specific criteria for an ergonomically designed chair. It's not just about aesthetics or looking comfortable for a catalog brochure. It needs a 5-leg base for stability. Why not 4?
A 4-leg chair can tip far too easily when a worker leans forward or reaches to the side because the center of gravity easily crosses the axis between 2 legs.
I've actually done that, fallen right over.
See? A 5-leg star base distributes the pivot point so that the center of gravity remains safely supported, regardless of how the worker shifts their weight. It prevents catastrophic falls.
The rules also mandate adjustable seat height and an adjustable backrest with lumbar support for the lower back. But here is the detail about seating that fascinated me the most.
What's that?
The rule says the padding on the seat pan should not compress more than 1 inch under the weight of a seated individual. Let me challenge this. Why wouldn't we want a super plush, sinking memory foam cushion? People pay extra money for the plush executive chair.
It seems counterintuitive, I know, but deep, plush padding is actually an ergonomic hazard. It comes down to the anatomy of the pelvis and the spine over a long duration. When you sit on a famed surface, one that compresses 1 inch or less, your body weight is supported primarily by the ischial tuberosities.
The sit bones at the bottom of the pelvis.
Correct. Those bones are designed to bear weight. But if the padding is too soft and compresses 3 or 4 inches, your sit bones sink deep into the chair. When that happens, the fleshy parts of your thighs and your hips end up bearing the load.
Which they aren't meant to do.
No. Furthermore, because your hips have sunk lower than your knees, the angle of your pelvis changes. The pelvis rotates backward.
And when the pelvis rotates backward, what happens to the spine?
The natural inward curve of your lower back, the lumbar lordosis, is completely flattened out. It might even curve outward into a kyphotic C shape.
Oh, that sounds painful.
It is. This places immense uneven pressure on the anterior portion of the intervertebral discs, pushing the gel center backward toward the spinal cord. Over an 8-hour shift, this causes profound lower back pain. Plus, deep padding acts like quicksand. It makes it difficult for the worker to subtly shift their weight and change postures, which locks them into a damaging static position.
So firm support is biologically much healthier.
Definitely.
That is a phenomenal explanation. So what if the job requires them to stand? The rules state you must provide floor mats or padded surfaces for prolonged standing, and ideally allow the worker to alternate between sitting and standing at their discretion.
Providing that variability is key. The human body is fundamentally designed for locomotion and movement. Being locked into a sitting posture for 8 hours is terrible for your cardiovascular system and spine.
But standing all day isn't great either.
No. Being locked into a standing posture is terrible for the venous return in your legs and causes blood pooling and varicose veins. Alternating between the two is the optimal biological goal.
Now, Rule 13 from this OSHA list is where things take a surprising turn, and it really highlights how broad the safety professional's vision needs to be. It says to eliminate or minimize the effects of undesirable environmental conditions.
Yes.
It lists excessive noise, heat, humidity, cold, and poor illumination. Now, as a safety professional, I understand why noise causes hearing loss and why heat causes heat stroke, but why are they listed here as ergonomic hazards?
That is a brilliant question, and it's a paradigm shift for many people entering the field. We tend to silo hazards, But these environmental factors are ergonomic hazards because they force the human body to unconsciously adapt its posture and movement in physically unhealthy ways.
Can you give me an example with, say, temperature?
Absolutely. Think about a worker in a refrigerated warehouse or working outside in the cold. Cold temperatures cause the body to restrict blood flow to the extremities to preserve core heat. The muscles and tendons become physically colder, stiffer, and less pliable.
Like a cold rubber band.
Exactly. In this state, a worker performing a standard physical task is much more susceptible to strains, sprains, and muscle tears because the tissue lacks elasticity. Furthermore, workers will naturally hunch their shoulders and tense their muscles to generate heat, creating a sustained, exhausting, static posture entirely caused by the environment.
Wow. What about excessive noise? How does noise change posture?
If a factory floor is excessively loud and a worker needs to hear an auditory cue from a machine, like a subtle click when a part is seated properly, or if they need to communicate with a coworker, what do?
You lean in.
They lean in. They crane their neck sideways toward the noise source. They contort their body to hear, abandoning their neutral posture and exposing their spine to awkward loads.
What about lighting? I know this is a huge issue in both manufacturing and office spaces. Why is poor illumination an ergonomic issue?
I see this constantly in the field, and it is almost always misdiagnosed. When lighting is poor, or conversely, if there is terrible glare on a screen or a gauge, the worker doesn't just sit back in their chair with perfect posture and say, oh, well, I can't see.
Right, they try to fix it.
Their biological imperative to complete the task takes over. They crane their neck forward. They squint. They lean their entire torso toward the work surface to see the fine details.
This creates a terrible, sustained, static posture. I've heard it called turtlenecking.
Yes, turtlenecking or forward head posture. And the physics of this are staggering. For every inch the head moves forward out of neutral alignment, the functional weight of the head on the cervical spine effectively doubles. Doubles. A normal head weighs about 10 to 12 pounds. If you crane your neck forward 3 inches to read a poorly lit gauge, the muscles in your upper back and neck are now straining to support the equivalent of 36 pounds of force.
Which leads directly to severe neck spasms, tension headaches, and upper back pain. And the tragedy is, a safety manager might see that worker rubbing their neck, and they might spend $1,000 trying to solve the back pain issue with a new ergonomic chair.
When the actual root cause of the biomechanical failure is a $5 burnt-out light bulb overhead.
Exactly. The whole system is connected. You cannot design the physical workstation without designing the environment it exists in.
You really can't.
So now that we have these overarching rules and the biomechanical physics behind them, let's apply them to the 3 specific workspace types you will be tested on: sitting, standing, and sit-stand stations. The exam requires you to know exactly when to assign a task to a specific posture. Let's look at Flieger's guidelines for this.
Let's start with sitting. The text dictates that a sitting layout is best for fine assembly, writing tasks, or intricate manipulation. It specifically notes there should be no handling of heavy items, no extended reaches, and it shouldn't require large downward forces.
Why is sitting so specifically limited to light precision work?
Sitting provides excellent stability for the upper body. Because your torso is supported by the chair, your visual and motor systems can focus entirely on fine, high-precision tasks like soldering a microchip or inspecting small parts. But there is a major trade-off.
What's the trade-off?
When you are seated, your legs are essentially taken offline. They cannot be engaged to help generate force or stabilize a heavy load. If you try to safely lift a heavy object or apply a massive downward force while seated, you isolate the biomechanical stress entirely on the vulnerable lumbar spine without the massive leg muscles to help.
So if there are heavy items involved, or if the worker needs to generate significant force, we must move to a standing station.
Correct. Flieger notes standing is absolutely necessary for manipulating heavy items, for tasks with extended reaches, and tasks requiring frequent movements between different areas of the bench.
You can use your whole body.
When you stand, your legs and torso act as a massive counterbalance. You can generate power from the ground up using the entire kinetic chain. You can also walk along a bench to reach things, completely eliminating the need to overextend your arms beyond that 15-inch limit we discussed.
And the third type is the sit-stand station. This is described as ideal for repetitive operations with frequent reaches.
The sit-stand station gives you the ultimate flexibility. It allows the worker to actively manage their own fatigue. They can sit to alleviate the static fatigue and blood pooling in their legs from standing, and then they can stand to alleviate the static compression on their spinal discs from sitting.
Okay, here is where we need to get highly specific for the exam and frankly for your daily practice. We need to talk about the height calculations for these stations. The expert sources are very clear about the rules for work surface height relative to the worker's body. Let's break this down.
This is a critical engineering metric. The elbow is the primary anatomical reference point for all workstation height calculations. Not the floor, not the shoulders, the elbow.
The elbow is king.
Let's start with tasks involving fine visual details. Think of a jeweler inspecting a gem or a worker assembling miniature electronics. For these high-precision, visually demanding tasks, the work surface must be placed above elbow height.
Above the elbow. Why? Because you need to bring the work closer to the eyes without forcing the worker to bend their neck down into that damaging turtleneck posture we just talked about.
Exactly. You elevate the work to meet the eyes, rather than lowering the head to meet the work. The forearms might be angled slightly upward, resting on padded supports, which is perfectly safe for light work. Now, contrast that with a completely different task. What if the task requires massive downward forces, heavy physical effort, or upper body strength while standing? For these tasks, the work surface must be below elbow height.
And we actually have a highly specific metric for this from the Bowen EHS practice questions, which reflects real-world engineering standards. The exam might ask for the appropriate bench height for work that predominantly involves the use of upper body strength from a standing position. The correct testable answer is 4 to 6 inches below elbow height.
That 4 to 6 inches is a critical number. Let's look at the physics of why. If a table is exactly at elbow height and you try to push down on something heavy, you are relying solely on the relatively small muscles of the triceps and the shoulders.
Right.
But if you lower the work surface 4 to 6 inches below the elbow, the geometry of the body changes. The worker can lock their elbows and lean in, using the entire weight of their upper body and torso to push down. They substitute body mass for muscular effort, which is infinitely more sustainable.
I love to use an analogy to remember this for the exam. Think of the jeweler versus the baker. Think of a jeweler inspecting a tiny diamond. They bring it up close to their face, well above the elbow, to see the fine detail without destroying their neck. But think of a baker kneading a massive, thick batch of dough. They need to lean their entire body weight into it to generate force. If the table was at their chest, they couldn't knead the dough.
No, they'd exhaust their arms instantly.
The table has to be well below their elbows so they can lock their arms and push. Jeweler up, baker down.
That's a perfect visualization. It permanently anchors the concept of force versus precision to the physical height of the bench.
So we've covered the factory floor, the heavy assembly stations, the lifting. But while industrial and field settings have very obvious, tangible physical hazards like cranes, heavy machinery, and massive loads, the modern safety professional also has to manage a much more subtle but equally dangerous environment.
Yeah.
The office.
And with the massive rise of remote work, this office environment has bled into people's living rooms, kitchen tables, and couches.
Oh, yeah.
The physical risks here are less visible than a spinning saw blade, but the cumulative trauma, the frayed tendons, the compressed nerves is very real and incredibly expensive for organizations. We need to look at the specific guidelines for office ergonomics from the OSHA 30-hour general industry source.
Let's start with the absolute basics of sitting posture in a standard office chair. The guidelines say the torso and neck should be vertical and perfectly in line with the chair back. The thighs should be horizontal to the seat cushion, and the lower legs should be perfectly vertical, reaching the floor. It's essentially creating a series of right angles at the joints.
We often refer to this as the 90-90-90 posture. 90 degrees at the hips, 90 degrees at the knees, 90 degrees at the ankles. When you achieve this alignment, your skeletal structure acts as a stacked column bearing the weight of gravity, rather than your muscles having to constantly fire just to keep your torso upright.
Now, what if the worker is using a standing desk in the office? The text says to stand straight, with the legs, torso, neck, and head approximately in one vertical line. But it adds a fascinating, highly specific detail. Elevating one foot on a small rest is an ergonomically acceptable variation of this standing posture. Why is that? Why would standing on one leg essentially be recommended?
It goes back to the anatomy of the lumbar spine. If you stand perfectly flat-footed with both legs locked for hours on end, it puts a constant static strain on your lower back. The pelvis tips slightly forward, which exacerbates the lumbar curve and compresses the facet joints in the spine.
Okay, so it pinches the lower back.
Exactly. But by providing a small footrest, maybe 4 to 6 inches high, and allowing the worker to alternate placing one foot on it, you subtly shift the angle of the pelvis.
It flattens the lower back slightly.
Exactly. Elevating one foot rotates the pelvis backward just enough to flatten the lumbar curve and relieve the physical pressure on those spinal joints. Furthermore, it introduces a vital micro-movement. By shifting weight from the left foot to the right foot over the course of the day, you are engaging different muscle groups and promoting venous blood return from the legs.
That is brilliant. It's a tiny engineering control with massive physiological benefits. Let's move up the desk to the monitor. The placement of the computer monitor must be at a comfortable distance. The goal, according to the text, is to reduce awkward postures, visual fatigue, eye strain, and neck and back pain.
We've talked about the neck pain from turtlenecking, but we need to discuss the eyes. The muscles in your eyes, the ciliary muscles, have to contract to focus on objects that are close.
Right.
If the monitor is too close to your face, your eyes have to over-converge and remain in a state of static muscular contraction. This causes profound eye strain, blurred vision, and severe headaches. If it's too far away or if the font is too small, you lean forward, you break that 90-90-90 skeletal alignment, you round your shoulders, and you put immense stress on your cervical spine.
So what is the ideal metric?
Generally, an arm's length away is the standard starting point. And the top of the screen should be at or slightly below eye level. You want your eyes to look slightly downward, about 15 degrees, because that is the natural resting position of the ocular muscles.
Okay, here's the part of the office ergonomics guidelines that absolutely blew my mind, and I really want to challenge you on this.
I'm ready.
Under a section titled Work Practice Controls, OSHA explicitly suggests using keyboard shortcuts like hitting Ctrl+S to save a document, or Ctrl+P to print instead of reaching for the mouse to click a menu. I have to push back on this. It sounds almost ridiculous that substituting Ctrl+S for a simple mouse click is considered an official, documented safety control. Are we really equating a mouse click to lifting an I-beam? Is the physical toll of moving a plastic mouse really that high?
I completely understand the skepticism. It sounds trivial, almost comical when you look at a single isolated mouse click. The mechanical force required to click a mouse button is practically zero.
Exactly.
But remember the definition of this field. Ergonomics is the study of cumulative trauma. It's not about the sheer force of one single action. It's about the frequency of motion, which is one of the primary heavily weighted risk factors for musculoskeletal disorders.
So it's the compounding effect of the micromovements.
Exactly. Let's trace the biomechanics. Think about how many times a data entry clerk, an architect using CAD software, or a graphic designer reaches from the keyboard to the mouse. They lift their hand off the keyboard, they externally rotate their shoulder, they reach out, they grip the mouse, they move it laterally using their wrist, they click with their index finger, and they return to the keyboard.
Okay, that's a lot of steps when you break it down.
They might execute that exact sequence of movements 3,000 times a day.
Which is roughly 750,000 times a year.
Yes. And each one of those motions requires microcontractions of the muscles and tendons in the hand, wrist, and forearm. The tendons are gliding back and forth through the carpal tunnel, creating microscopic friction. Over thousands of hours without adequate biological recovery time, those tendons become inflamed. The synovial sheath surrounding the tendons begins to swell from the friction.
And then it compresses the nerve.
As it swells, it compresses the median nerve. That leads to pain, numbness, tingling, and debilitating conditions like tenosynovitis or carpal tunnel syndrome.
Wow. When you multiply it out, the biological cost is staggering.
By teaching a worker to simply use Ctrl+S instead of reaching for the mouse, you eliminate the shoulder rotation, you eliminate the grip exertion, and you eliminate the lateral deviation of the wrist. You keep the hands in the neutral, optimal typing posture. You are engineering out literally thousands of hazardous micromovements every single week. That is the absolute essence of an effective work practice control. It costs $0, but it saves thousands in medical claims.
That is an incredible reframing of how safety professionals need to look at danger in the workplace. The hazard isn't just the heavy box or the spinning gear, it's the invisible thousands of tiny movements. And identifying these microhazards requires a systemic, programmatic approach. You can't just fix one desk, tell someone to use Ctrl+S and walk away thinking the job is done. You need a permanent solution integrated into the company.
Which leads us to the final major area you need to thoroughly understand for the exam and for your career. The MSD prevention program, often called the Ergonomics program, and the safety professional's role within it.
The sources insist that this program must be a continuous process. It's not a one-time audit that you put in a binder on a shelf. It is a living, breathing system within the organizational culture. And who's involved in this system? The text is absolutely adamant that it requires cross-functional teams.
You cannot do ergonomics in a vacuum. If a health and safety professional sits in an office and tries to redesign a workstation without ever talking to the people actually doing the work, the intervention will fail.
Right.
The sources list exactly who needs to be at the table. Managers and supervisors to provide funding and resources, health and safety reps to provide the scientific data, technical specialists and engineers to design the fixes, maintenance personnel to install them, purchasing agents, and crucially, the worker and union representatives.
Purchasing is a really interesting one to include on a safety committee. Why are the buyers at the table?
Because purchasing agents are the ultimate gatekeepers of the physical environment. If they are incentivized solely to save budget, they might buy cheap, non-adjustable chairs or heavy, poorly balanced hand tools. If they do that, they are introducing massive ergonomic hazards into the facility before the equipment even comes out of the box.
Oh, that makes total sense.
By integrating ergonomic standards into the purchasing policy, meaning every new tool must meet specific weight and balance criteria before it can be bought too. You prevent the hazards proactively at the source.
That is proactive ergonomics on a corporate scale. Now, what about the workers themselves? The text makes it clear that workers aren't just passive subjects receiving ergonomic interventions from on high. They have specific active duties in this program.
They do, and a successful program relies on them. Their duties include using the internal ergonomics program to review their physical work area when they are first hired. They must request reviews when their tasks or tools change. They must actually use the tools and equipment properly. An expensive, highly adjustable chair does absolutely zero good if the worker never touches the levers to adjust it to their body.
Right.
And perhaps most importantly, they have a responsibility to report when equipment is degraded or when they start experiencing the very early, subtle symptoms of an MSD.
Early reporting is vital. If they wait until their hand is completely numb and they need surgery, the prevention program has failed. Now, let's look at the toolkit the safety professional uses to manage all this data. How do we objectively prioritize which hazards to fix first?
The sources outline a wide array of assessment tools, scaling from simple to highly complex. At the foundational level, you have simple, employee-led checklists. These empower the workforce to identify basic hazards themselves, answering questions like, is my monitor at eye level, or am I reaching above my shoulders more than 10 times an hour?
But then it scales up to highly complex quantitative engineering analyses. The exam blueprint specifically names the NOH lifting equation. We aren't going to do the calculus here on audio, but you need to understand its purpose and what it measures.
The NOH lifting equation is an objective mathematical tool developed by the National Institute for Occupational Safety and Health. It is used to calculate and quantify the exact biomechanical risk of manual material handling tasks. Instead of just looking at a box and guessing if it's too heavy, the equation takes into account multiple variables.
What kind of variables?
It looks at the actual weight of the load, how far the worker has to reach horizontally to grab it, how low or high the lift vertically begins and ends, the frequency of the lifts per minute, the quality of the hand coupling or grip, and the asymmetric angle, which is how much the spine has to twist during the lift.
And when you plug all those variables in, what does it give you?
It calculates a recommended weight limit, or RWL, for that specific unique task. It tells you the exact maximum weight that nearly all healthy workers could lift over an 8-hour shift without increasing their risk of a lower back injury. It spits out a number that tells the safety professional, this lift under these specific conditions is safe, or this lift is virtually guaranteed to cause a severe back injury over time. It moves ergonomics completely away from subjective complaints and into the realm of undeniable, objective data.
It's incredible. Looking at all of this, the anatomy, the engineering layouts, the office micro movements, the NIOSH math, my biggest observation is how this field requires the safety professional to be a complete chameleon. You have to deeply understand human anatomy and synovial sheaths. You have to do mathematical risk calculations based on load constants. And you have to act as a persuasive consultant to architects, CEOs, and purchasing agents before a facility is even built. You're literally shaping the physical world to protect the biological limitations of the people in it.
It is without a doubt one of the most intellectually demanding and tangibly impactful roles in any modern organization.
Okay, let's summarize exactly what we've covered today. Passing Domain 3, Topic 4 on the ASP exam requires a deep, integrated understanding that ergonomics is a proactive, data-driven science. It is the science of fitting the workstation, whether that is a complex manufacturing bench, a rugged construction site, or a remote office desk, to the biomechanical limits of the human body. We discussed the catastrophic dangers of static effort and awkward postures restricting blood flow. We broke down the 4-component layout principles to choreograph work. We explored the critical height calculations, the jeweler versus the baker for seated and standing work, and we examined the need for a continuous cross-functional MSD prevention program.
And for the exam, remember the key quantitative metrics. The 15-inch maximum reach radius, ensuring the pivot point is at the elbow rather than the shoulder, and keeping work surfaces 4 to 6 inches below the elbow for tasks requiring heavy downward force.
Absolutely. Those are the numbers that will show up on test day. Before we wrap up, I want to leave you with a final provocative thought to mull over as you study. We talked extensively about anthropometry, the statistical study of human dimensions as the absolute foundation of our workspace design. We use this historical data to determine the reach radius, the height of the desks, the size of the chairs, and the width of the doorways. But the source text mentions an unavoidable truth. Work-based design must reflect changes in demographics.
Yes, human populations are not static entities. They evolve.
Exactly. With the global workforce aging rapidly, meaning we have older workers on the floor with naturally decreased joint mobility and strength, and bodies physically changing generation by generation due to diet, lifestyle, and healthcare, the average human is simply not the same size or shape they were 40 years ago when many of these baseline tables were created. So the question is, will the baseline anthropometric data we rely on today become dangerously obsolete? And how will the safety professionals of tomorrow have to radically redesign the standard adjustable workstation to fit a completely different, unprecedented average human body? It's a complex demographic puzzle that the field is going to have to reckon with very soon.
It's a fascinating challenge. The target is always moving because the human body is always changing.
It really is. Thank you so much for joining this session of QHSE Talks. Keep studying the blueprint, trust the science, and remember the golden rule. We don't fit the person to the job, we engineer the job to fit the person. See you next time.